Honorable laureates, Yours Excellencies, distinguished colleagues, members of the Academy, ladies and gentlemen. This year's Nobel Prize in Chemistry is all about batteries and how to convert chemical energy provided in a very lightweight, compact and high capacity form into electricity, and vice versa, and by doing so, creating a rechargeable world. Now, the development of efficient rechargeable batteries is a very daunting and difficult task. And everybody who has been working with batteries knows that it's really, really very hard and arduous to find solutions to fit all the pieces of the puzzle together in combination to get a good battery configuration, and especially then the rechargeable ones. Nevertheless, our three laureates, John Goodenough, Stanley Whittingham and Akira Yoshino, they addressed this challenge, this very daunting challenge, and they made very crucial discoveries that eventually led to the development of the modern lithium-ion battery. This battery is indeed a remarkable battery, and it has changed our world quite dramatically. It's been a large part behind the so-called mobile revolution, where we actually have access to our mobile devices wherever we go and wherever we want and whenever we need them. It's also a large part behind the switch we are witnessing in the transport sector, where we now increasingly use electrically driven vehicles. Even large vehicles like large trucks and even aircraft can now be powered by lithium-ion batteries. And moreover, the lithium-ion battery is also increasingly used as a complement for renewable energy sources that fluctuate over time, like wind and sunlight, and thereby facilitating the use of such renewable energy sources. Thus, we can now increasingly access electricity without access to the grid, wherever we are and whenever we need it. And this has indeed changed our lives dramatically. In a sense, this prize has its origin already almost 200 years ago now, or around 200 years ago. And as mentioned earlier today by our president, Dan Larhammar, we heard that the young chemist, Johan August Arvidsson, he discovered the metal, the element lithium, together with his advisor or mentor, Jöns Jacob Berzelius. They discovered this element from a mine on an island not far from here, the Ute island in the Stockholm archipelago. And the two scientists also proposed a name for this new element, and they chose the new name from the Greek word of lithos, meaning stone or rock. So maybe in that sense, it's fair to say that our three laureates are the true rock stars of battery science and technology. Okay. So let's first with our first laureate, Dr. John Goodenough. So Dr. John Goodenough, he was born in 1922 in Jena, in Germany, of American parents who actually lived in the UK at the time. And later on, he moved back to the US. And in 1952, he received his doctoral degree from the University of Chicago in Illinois. And since 1986, he is now very active, I should say, as the Virginia H. Cockrell Centennial Chair in Engineering at the University of Texas at Austin. And he is indeed very active in coming to work every day, working on the future of the lithium-ion battery. We are indeed very grateful and happy that Dr. Goodenough is with us here today. He's here in the audience. However, he has chosen to record part of his presentation, and the presentation will be presented by one of his close colleagues, Dr. Arumugam Manthiram. Please join me in welcoming Dr. Manthiram up on stage.
Thank you, Dr. Ramstrom. Good morning. Honorable laureates, Your Excellence, distinguished guests, ladies and gentlemen. I am humbled to take you through this presentation on behalf of 2019 Chemistry Nobel laureate, Professor John Goodenough. I was Professor John Goodenough's postdoctoral fellow for 6 years, both at the University of Oxford in England and then at the University of Texas at Austin. Since then, for the past 28 years, I have been his faculty colleague just down the hall from his office at the University of Texas at Austin.
Sciences for this recognition. I thank you very much. In the early 1970s, there was a problem of exposing the dependence of the Western world on imported oil. So we were interested to see how one could use alternative energy sources in order to be able to wean ourselves from our dependence on fossil fuels. What is there about the lithium-ion battery that is useful? Well, first of all, it has an LiCoO2 cathode, which is high voltage cathode, and therefore it allows you to have a carbon anode instead of having lithium as an anode, where you get dendrites and so on. So you can get a dendrite-free cell. You know, when I first said we get a very high voltage with the LiCoO2, immediately there was a gentleman in Japan by the name of Akira Yoshino who said, what you need with that material is a carbon anode. And so for that, we developed the carbon and, and lithium cobalt oxide as a cell, which was he demonstrated for the Sony Corporation, and the Sony Corporation decided that would make a very good system for launching the wireless revolution. So they developed the battery, the lithium-ion battery, for launching the wireless revolution.
So lithium-ion batteries have touched each of our lives by enabling the revolution in portable electronics, including the cell phone and laptops. They are on the verge of transforming the transportation sector through electric vehicles. They are also beginning to enter the utility industry to enable the utilization of renewable energy sources such as solar and wind energies. But all these became possible because of 30 years of work on transition metal oxides by Professor Goodenough, beginning from 1950s to 1980.
Well, it so happened that I was put in charge of what was left of a ceramics laboratory. And so I thought I would use that opportunity to try to solve some physics questions because I had a background in physics, but I wanted to use chemistry to see if I could probe and answer some questions with chemistry. Magnetic materials for the first ROM memory was quite a challenge because for that we had to develop in a ceramic a square BH loop, which is a hysteresis loop, and that was normally done by rolling a metallic tape, but you can't roll a ceramic. And so the problem was, how do we develop a square hysteresis loop in a ceramic? And it was a bit of a trick, but I learned a fair amount of chemistry in the process. Well, one of the things that was really quite important is that the atoms have orbits, and they have certain spatial configurations. And the cooperative atomic orbital ordering gave rise to certain structural changes that were very important for the crystallographers who were trying to understand why things had certain phase changes. By the sign of the magnetic interactions, you see, are they going to be ferromagnetic or are they going to be antiferromagnetic? And if you want to design a magnetic material or understand why a material such as LaMNO3 has ferromagnetic interactions in the basal planes and antiferromagnetic interactions along the z-axis of what seems to be a quite symmetric cell, then it's very important to lead to the whole business of orbits, orbital ordering, and so on. It all fits together. People had invented the idea of a high-temperature battery, which would consist of molten sodium as the anode and sulfur attached to a carbon paper as the cathode. And it operated about 300 degrees centigrade, and they used a sodium-ion electrolyte for that, and so it raised the question, how do you design a sodium-ion solid electrolyte? And we came up with the NASACON structure, where the NASACON stands for sodium, which is Na, superionic conductor.
So Professor Goodenough's work on oxides involved the development of first random access memory for digital computers, understanding of the cooperative atomic orbital ordering and magnetic interactions in materials, and then the development of a solid sodium-ion electrolyte. These studies laid the foundation for the development of oxide cathodes for lithium-ion batteries in the next century, beginning in 1980. So how does a lithium-ion battery work? The lithium-ion batteries have three major components: a negative electrode called anode and a positive electrode called cathode. They are separated by a polymeric separator soaked with liquid organic electrolyte. During charge, the lithium ions move from the cathode to the anode internally, while the electron moves from the cathode to the anode through the external circuit to balance the charge. During discharge, or when we use the cell phone or drive an electric vehicle, the lithium ions move from the anode to the cathode internally, while the electrons move from the anode to the cathode through the external circuit. This means the electrolyte here should allow the charges to move only in the form of lithium ions, while the external circuit with a copper wire or an aluminum wire should allow the charges to move only in the form of electrons. That means the separator should be a good lithium-ion conductor, but should be an electronic insulator. That's all wonderful, but how do we get energy out of this process? So during charge, the electrons move from the cathode to the anode with the supply of electricity from an electrical outlet. During discharge, the electrons flow from a higher energy level from the anode to a lower energy level at the cathode, and the energy released during that process is taken out as electricity to power our cell phone or to drive an electric vehicle. So, to maximize the cell voltage, the cathode energy level should be as low as possible, and the anode energy level should be as high as possible, because the voltage is the difference between these two energy levels. However, there is a constraint. The energy levels of cathode and the anode should lie within the band gap of the electrolyte, separated by the LUMO and HOMO. LUMO means lowest unoccupied molecular orbital of the electrolyte, and HOMO means highest occupied molecular orbital of the electrolyte. On the other hand, supposing if the LUMO lies below this level, then when we charge, we will put the electron from here to the LUMO rather than here, and that can lead to the leakage of electron internally and short circuit. Finally, you can notice during charge, the voltage slightly slopes upwards because the energy difference between these two are increasing. During discharge, exactly the opposite happens because the energy difference between these two are decreasing. Although the operation looks very simple, there are several criteria that needs to be considered to design a good battery.
First, it's got to be low cost. Second, you got to be able to store as much electric power as you can, and therefore have a very big energy density. Third, you're trying to, in the battery, store electric power, and the power is the current times the voltage. So you need as big a voltage as you can at as high a current as you can do. And you want big capacity and a high current. Cycle life. Well, you don't want the thing to conk out if you can't do at least 1,000 cycles in your battery. So the idea is you don't want the amount of power that you can store decrease too fast each time you have a cycle in the battery. Of course, safety is terribly important, and you have in the electrolyte a flammable organic electrolyte, and so you don't want there to be an internal short circuit that will cause a safety problem. Then, last of all, when you're through with them, you don't want to have them contaminate the environment. You like to be able to recycle the material or to do whatever you can so that you don't find yourself just putting a lot of junk in the environment.
So these 6 factors are controlled by the materials we select to design a battery. So let us take energy density as an example. Energy density is in part user time. That means how long we can use a battery before we charge. And user time or energy density is determined by the product of 2 factors. the amount of lithium ions we can store in a given weight or given volume times the cell voltage we get from a cell. And that is determined by the energy difference between the anode and the cathode. So to maximize the cell voltage, the cathode should be cathode energy should be as low as possible. With transition metal ions, the energy levels will be lowered as the oxidation state increases. For example, vanadium 3 plus here, 4 plus here, 5 plus here. So the question is, how do we access these higher oxidation states so that we can get a high enough voltage and then higher energy density? So the rechargeable lithium batteries were initially developed with sulfide cathodes by Professor Stanley Whittingham at Exxon Corporation in the United States.
In the early days, people were reversibly inserting lithium between the MS2 layers of sulfides. So that was the idea. And when you insert between layers, it's called intercalation, meaning that intercalation means insertion between layers, okay? And so they had TiS2, and the people were examining the chemistry of lithium insertion extraction from TiS2 back in the 1960s.
There were two major issues with the sulfide cathodes. First, we cannot get more than 2 or 2.5 volt. Second, the sulfide cathodes did not contain lithium ions in them. Therefore, one has to use lithium metal anode that posed safety concerns, fire hazards. In fact, there were attempts to put lithium batteries containing lithium metal as the anode into the market, but then they were abandoned in the 1980s because of fire hazards.
And it was very clear to me that you needed to have a higher voltage in order that you could do something with the anode problem. And therefore you had to go to an oxide as against a sulfide. So I looked at oxides and managed to figure out how to have a high voltage cathode with an oxide instead of a sulfide. Then we could play around with the anode side.
So, if you take the sulfur 3p band, it lies at a higher energy. So that means it's difficult to access these higher oxidation states, for example. Therefore, the voltage we get is limited by the top of the sulfur 3p because we cannot go below. On the other hand, the oxygen 2p orbital, the top of oxygen 2p lies at a higher energy. Therefore, we can easily access higher oxidation states like cobalt 3 plus and cobalt 4 plus. So that can push the voltage from less than 2.5 to, for example, as high as 4 volt. This basic idea led to the discovery of 3 classes of oxide cathodes by Professor Goodenough in the 1980s, involving 3 postdoctoral researchers from 3 different parts of the world who were fortunate enough to work with him in the 1980s. And they were Mishishima from Japan on the layered oxide, Michael Thackeray from South Africa on the spinel, and myself from India to work on polyanion cathodes. The first family of cathodes Professor Goodenough's group developed was a layered oxide.
I started with lithium cobalt oxide because it was a layered compound with ordering of the lithium and cobalt in alternate layers. And I understood, or I investigated how much lithium I could take out of the lithium cobalt oxide before it changed its structure. And I found I could take out over half of the lithium from the lithium cobalt oxide without us changing its structure, and I could have therefore a reversible lithium insertion extraction oxide as against lithium insertion extraction sulfide to give me higher voltages.
So lithium cobalt oxide solved two problems. First, it increased the voltage from less than 2 or less than 2.5 in a sulfide to 4 volt. Second, the cathode as synthesized contained lithium in it, so no need to have lithium in the initially assembled cell in the anode, enabling the use of or enabling the elimination of unsafe lithium metal with graphite anode that was carried out by Nobel laureate Akira Yoshino. However, there was one issue. Cobalt is less abundant and more expensive, so the next cathode material involved was a manganese oxide, spinel oxide. Manganese is abundant and it is 100 times cheaper than cobalt.
Well, I started with the lithium cobalt oxide, and then a man from South Africa by the name of Michael Thackeray came to my office in Oxford and said, I want to use the magnetite because that's a cheap material for lithium insertion extraction. And I said, well, I would like to see if you could do it in my laboratory because normally the spinels are line phases, and so I'm surprised that you can put lithium in and out of magnetite and still have the same structure. So he did that in my laboratory, and then I said, well, that's fine, but what you need to do is to go to a manganese material so you can put the lithium in and out without having to push some of the lithium out as a separate phase on the surface. So that's how Mike Thackeray and I started to work on the lithium manganese oxides.
The two classes of materials we saw earlier were simple oxides. So they are prone to lose oxygen from the lattice under the conditions of short circuiting or higher temperatures. So the third series of oxides explored were polyanion oxide like iron sulfate, in which the oxygen is bonded very tightly to the sulfur anion in the polyanion, so they offered better thermal stability.
There is a so-called inductive effect in which you get a very strong sulfur-oxygen bond in the sulfate, and that is able to reduce the energy of the iron 3, iron 2 plus redox couple, and so I wanted to be able to get a higher voltage, and so I wanted to be able to lower the energy of the iron 3 plus iron 2 plus redox couple, and so you go to a sulfate. The sulfur has a strong sulfur-oxygen bond, and that then makes you have a more ionic bond with the iron, and lower the energy of the iron 3 plus 2 plus couple and increase the voltage.
So the polyanion oxides offered yet another way to increase the voltage from an oxide to a polyanion. For example, the voltage increases from less than 2 volt from a simple iron oxide like Fe2O3 to 3.6 volt when we go to the polyanion iron sulfate. Recognizing the advantage of polyanion or the inductive effect to increase the voltage, 10 years later, in 1997, another polyanion cathode called olivine was developed.
The question is, do you want three-dimensional insertion of the lithium? Or in this particular case, you had one-dimensional insertion, but fortunately, that material comes as flat plates so that the plates are rather thin, so you can do one-dimensional insertion extraction in the iron phosphate.
In summary, a fundamental study of the properties of transition metal oxides led to the identification of 3 classes of cathode materials for lithium-ion batteries. The discovery pushed the boundaries at the intersection of solid-state chemistry and solid-state physics. These 3 classes of materials, namely layered oxide, spinel oxide, and polyanion oxide, still remain the only viable cathodes for practical lithium-ion batteries. And they also serve as the basis for future development. So as we move forward, we have an obligation to give a cleaner planet to our children and grandchildren, liberating them from the dependence on fossil fuel.
How can we liberate modern society from its dependence upon the energy and fossil fuels? And that is something we would like to be able to do. We would like to be able to use the energy from the sun and store it in the batteries so that then we could have stored electric power in the battery and emancipate ourselves from the energy stored in a fossil fuel, because when you burn the fossil fuel, the CO2 goes into the atmosphere and contributes to global warming and all the other problems we have. First of all, we have to learn to harvest the energy that comes to us daily from the sun, and that's really rather dispersed. Now, nature does it in plants and trees, but we'd like to find another way to do it. So we would like to take the wind energy and the radiant solar energy, which you can convert into electric power, and store it in a battery. With the flammable liquid electrolytes that you have in today's batteries, if you have a short circuit that goes through as a result of lithium dendrites that penetrate from the anode to the cathode, that short circuit the battery, you get a fire. And you don't want fires on the roads. You don't, I mean, that's a safety hazard. It is important to find out how you can plate and strip an alkali ion anode in the battery that does not grow dendrites.
So the task of developing affordable, safe, long-life batteries with higher energy and power density is in front of us. And I think interdisciplinary research involving both basic science and engineering will guide the way as we continue our journey.
I like science because we believe that by doing fundamental research, we can find applications that will be very useful for society. And I think curiosity is very important. And so being able to satisfy your curiosity is fun. Is science fun? It's hard work, but it's satisfying when you get a good answer.
So, I would like to thank all the students, postdoctoral fellows, scientists, and engineers who worked with Professor Goodenough for 7 decades in 3 different institutions. I would also like to thank the Nobel Committee and the Swedish Academy of Sciences for bestowing this highest honor on Professor Goodenough. Finally, I thank Stockholm University for hosting these Nobel lectures. Thank you all.